much time we got? 22 minutes. So, it's really only been in probably the past 200 years that there's been a great deal of experimental evidence that has been used to support our atomic model, the quantum model. Okay, and they're continuing to come up with more and more things, like the subatomic particles. And we're even not still going to talk much about the subatomic particles. You guys know what I mean when I say the sub?
Quarks.
Quarks, gluons.
Quark gluon pop.
No, we're not going to talk about that either.
I learned about that in freshman year. We
Yeah.
didn't really explain what it is.
Yeah, no, I don't really know what it is.
Okay.
Yeah. One of the most striking things about the chemistry of elements is the periodic repetition of its properties. Okay, and you guys are familiar with the periodic repetition of how the periodic table is arranged, and give me some things that are repeat themselves when looking at the periodic table.
Families.
I mean, like, how they're
Yeah, kind of.
I mean, they're family.
electronegativity.
Okay, so there's a trend that's fairly smooth when it comes to, like, you don't have like a random guy right here that's like extremely electronegative, and then the guy next to it, it's the opposite, right? You can say that about any of the trends. Radius trend, ionization trend, which we haven't reviewed that yet, I don't think, in this class. Have we gone over all the trends yet, other than maybe discussing electronegativity? That's coming. I don't know if that's this chapter or not. Okay. There are several groups of elements that show great similarities in chemical behaviors. Do you guys remember what determines the similar chemical and physical behaviors? You should. What determines that? Why do things tend to experience have similar chemical and physical properties?
The amount of protons.
No.
Valence.
Yes, valence electrons.
Okay.
Yep. Yep. So, we're going to spend a little bit of time talking about light, because electrons have very much similar properties to that of light, along with some other things. We will talk on Monday. We will talk in great detail, or not great detail, but we will talk in detail about the wave-particle duality. You remember that?
I remember
The fact that an electron acts like a wave and a straight line photon at the exact same time.
Yeah. Yes.
But guys, electrons are really, 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 really difficult to wrap people's minds around. Okay? What we've noticed is that the bigger the object, the more it acts like a photon. So if I have a basketball and I throw it, it's not moving like a wave. But there are people that would argue that it does have some wave-like properties, but most of it is photon-like properties. And then when you get really, really small things, like light, it almost predominantly acts like a wave. But there are things that suggest that even light acts like a straight line. And then you've got electrons, and that falls smack dab in the middle of that mass spectrum. Big things act like photons, really small things act like waves, and guess what plops right in the middle of the size spectrum? An electron. Okay? So we need to talk a little bit about the electromagnetic spectrum. Electromagnetic radiation. You guys should be familiar with these three, at least a little bit. Emily probably more than the rest of you, because she took physics already. Okay? So electromagnetic radiation is any radiant energy that exhibits wave-like behavior and travels through space at the speed of light. Now, the reason why it says in a vacuum is because they all wouldn't travel at the same speed if there was air particles or air resistance. Because not everything is the exact same size. Okay, but assuming you take away all the air particles and any forces acting on it, and it were just going through a vacuum, everything wouldn't move at the speed of light. That's electromagnetic radiation. For example, radiant energy, or energy in the form of heat, wouldn't move as fast as light does in a vacuum. Because isn't radiant energy or things that warm the oven that usually come from some light source like fire? Okay? So here are the things that make up electromagnetic radiation. They all have wavelengths, they all have a specific frequency, and they all travel at the speed of light in a what? Vacuum. Now you don't have to memorize this number, I'll make it easy for you. How about that? A little bit easier. So we're going to use that number instead of the 2.9979. Cool? Alright. Open up your books to page 286.
Let me just a second.
Yeah, sorry. 286. Let's just quickly review. For some of you, this might be new, I guess. But let's go over all the vocab here that goes into electromagnetic radiation. Now, I'm not going to get too crazy into this, but actually, really what causes electromagnetic radiation is two field forces. Those two field forces are electromagnetic, or electric field and a magnetic field. So actually, light gets propelled through air, through space, by an oscillating electric and magnetic field. So like an electric force creates a magnetic force, creates an electric force, creates a magnetic force, and that's actually how light or anything on the electromagnetic spectrum moves through the air. It's through a field force. There's no contact at all. It's really quite interesting to get into that. We don't get too crazy into that, but it's pretty cool stuff. So let's review some things. Might want to put this in your notes. It wouldn't be a bad idea somewhere. So, wavelength by definition is what?
The length of the wave is between the radiation.
Distance between peak and peak, or trough and trough. Should be the same. So peak. How do you spell trough?
TROUGH.
Okay. Alright, so peaks are the top part, troughs are the bottom part, should make sense. Top of a hill, valley, and so forth. Okay? But the distance from peak to peak or trough to trough is called the wavelength. Another thing that might not be something we talk too much about, but it's important, would be from the center of the wave to the peak, or from the center of the wave to the trough, is called the amplitude. And that's really the strength of your wave. The higher your peak or the lower your trough, the more powerful your wave is. Okay? Now, frequency is dependent on time. Why? Okay, so it's really how many cycles you get through the wave per unit time, and usually per second. And instead of me drawing some more stuff up here, if you guys look in your book on 286, you guys all there? On the day. You guys should see the three pictures at the top. Notice at the very top it says 1 second. So what that's trying to refer to there is that all of those are the wave patterns of different waves every for a 1 second period. Okay, now notice they all look like waves. They all have the sine wave function, but some of them appear to be more compressed than others. Yeah. Okay. So what this simply means is when we start talking about frequency, it's really how many cycles through the wave we get per unit time. So which one has the highest frequency?
The third one, the blue one.
The blue one, the bottom one. It has more cycles over the same time period as the two above it. Now, what is the relationship between wavelength and frequency? Any ideas?
The wavelength is smaller.
Yeah, it's an inverse relationship. So the more cycles you have, the smaller your distance between them will be. And it's a nice inverse relationship. So I think you guys have in your notes of the equation for this.
Yeah.
So you guys have C equal like oops. You have that? Everyone? Okay, this is your frequency. This is your wavelength. And if this goes up, this goes down to give us a constant. And what do you think C is? Speed of light. Now we're going to assume everything's in a vacuum. Following so far, this should come back pretty easily for you, yeah? For the rest of you, this might be completely new. Or you maybe have heard about these words, but we've never really done it. Right? I'm assuming? Because I don't think in chemistry we ever talked about this.
Isn't this the frequency is how high it goes in
I don't think so.
Energy equals gravity times speed.
I could be wrong. If you find it, let me know. But I'm almost positive that amplitude is just the displacement away from equilibrium. So, unless you want to say that there's a different word because it's a negative displacement. But yeah.
Can M be used to mean gravity?
M,
Yeah. The gravitational force.
usually we refer to gravitational force as weight or FG.
Okay.
We use a lot of times G to refer to the magnitude of acceleration of gravity.
So what's the big old M used for that?
When we were doing, you're talking about when we were doing in physical science,
Yeah.
figuring out gravitational force.
Yeah.
So that was the equation used to figure out the gravitational force between two objects. So we had big M and little m. Big M just referred to the bigger mass,
Okay.
and little m referred to the smaller mass. For example, I could figure out the gravitational force between me and Grant right now.
Yeah.
It would be extremely small because our masses are small. And the reason why the gravitational force is much bigger between us and the Earth is because the Earth is so stinking big. That makes sense. The bigger the object, the more gravitational force you'll have. Okay? What else? Oh, on that same page, you should see the spectrum of light. Okay? Everyone at the bottom, everyone see that? Okay? And you should see the bottom appears to be your, it doesn't say anything on the bottom. But anyway, so it just shows you the wavelengths. You should be familiar with most of these, but all of these are light. I know it's kind of difficult for us to comprehend that an X-ray is really light, but X-ray is light. We just can't, our human eyes cannot see that form of light. Our human eyes can only see what form of light?
Visible spectrum.
Yep.
What you see is application to visible light.
Yeah. Okay? So, microwaves, radio waves are really just light. I know it's weird. I mean, when I first saw that, I thought that was kind of goofy, you know? I didn't really understand that. But they're just different frequencies and different wavelengths of light. So really, when you heat up your food in a microwave, you're just shooting light bolts at it. What's really happening, guys, when you heat up your food in your microwave is you're setting microwaves into your food. It's vibrating the water molecules inside your food. It's transferring energy to the water molecules inside your food, and then due to conduction, it's heating up the rest of your food. Okay?
Kind of listen.
What?
I think they're kind of late.
So I
Different
think
kind of
wave?
Honestly, it's actually the thing.
What's that? Brainwave?
I think it's
Like if they're white light
So
waves?
any wave of light.
How are potato things going to warm up?
And sound wave or radio
Sound,
wave?
sound
We
waves
said
are,
radio wave.
yeah, but that's not this. So radio waves and sound waves are different. So radio waves are light waves that get transmitted to your radio. Your radio transfers that energy to sound waves. So sound cannot travel through a vacuum because sound has to have a medium that it transfers the energy through. I know it's kind of weird, but if I were to put your cell phone in a vacuum and we were to call it, we would not be able to hear it. Because it needs some sort of vibrational source or object to move through.
Like in space, you can't hear anything until you touch them. Like you can't hear another astronaut until you touch their helmet.
Oh, I didn't know that.
Yeah. The intercom, but if you like grab their shoulder, which you probably shouldn't do with clumsy gloves in space, but if you like they touch each other, helmets to each other, or if they touch hands.
That's interesting.
It
Huh, that
travels
makes sense.
too.
I just never thought about that.
It travels with the suit, yeah.
Yeah. So the vibrations that they're making in their vocal cords and
Yeah.
move through their body and up to the other person. That's cool.
They have like a radio, I'm sure, that like connects somehow. So
Sure.
Through the ship, probably.
Yeah, probably. Probably better ways than just touching.
Yeah. Yeah. But
You keep looking at the clock there, Annie. What's going on here?
Yeah,
What'd you find out?
not.
Brainwaves or infrared waves? Huh.
pretty cool.
Who told you that? Or who told you? Oh, I didn't. I'm asking like, who told you the idea? Was that in psychology or something?
No, it was on the Odyssey.
Oh, really?
About converting radio waves to brain waves.
Oh, that would be really weird if
For
you could
mind
like.
control.
I don't think that's possible.
Then again, too.
I don't know if I would get my scientific theology from Odyssey. But-
That's why, I don't know if they told me.
Adventures in Odyssey?
Oh. Wait, like what? Like Whitman or Whitaker? I mean.
Yeah, Mr. Whitaker.
Okay, that was okay.
Yeah.
Yeah. I was
You guys,
thinking-
you
I
guys
was
are
thinking-
too. You guys are too young to.
No, I know,
I was
Adventures in
just-
Odyssey, but when you were saying
I just
Odyssey,
knew
I'm
the
like, you haven't seen.
what is he? He's like the old wizard in a lot of stories. He's like the advice giver guy. Mr. Whitaker.
What was the nerdy guy with glasses? Like,
Eugene?
Eugene.
Yeah.
Ryland's Eugene.
That's not nice.
I always viewed him as a curly-headed guy.
Yeah, like taller than I
Yeah.
I'm not that tall, Emily.
No, not you, that's what I mean.
Okay.
Okay, so we got this. Oh, it's really important. Wavelength always is going to be in a meter unit. Actually, most often you'll be given it in nanometers because that's typically what wavelength is in. So you'll have to convert nanometers to meters before you use this equation. Second off, a hertz is really just an inverse second, or a second to the minus 1. So this is how this works. If you got your equation here, this is going to be in meters. You're going to have to convert it from nanometers. And then this is a 1 over a second, which is an inverse second. That's how we get a meter per second speed of light. Okay? That's where that comes from. Now, I want you guys to do this next problem here to finish out the day. And there's a lot of fluff here that you probably don't need, but a brilliant red color seen in fireworks are due to the emission of light with wavelengths around 650 nanometers. Okay, and then it tells you certain salts and how you can see it. Calculate the frequency of red light of wavelength 6.50 times 10 to the second. You will need to convert that nanometer number into meters. You guys know the convert. Yes, good. See, every once in a while this stuff pays off.
Zero rays, millennials, many
Was it millennials?
Yeah, because that goes with millimeters. Century is.
Centi. What was the top half? Or did we just do the bottom half?
No, it was like Molly killed Harry's dirty dog.
Oh, mega, kilo, hecto,
Jessa.
decadessa, or decadessa,
Really large.
deci. And then tight pants be lame, tight pants be lame. That'll be coming up in a couple chapters.
Yes,
But then we gotta name an acronym for the 8 other ones that I'm gonna give you. Trigonal, bipyramidal,
Okay.
octahedral.
What if we use the speed of light equation?
Yep.
That equals. It'll be times 2.
So your speed of light could be your 3.00 times 10 to the 8th meters per second. And your wavelength should be 6.5 times 10 to the -7. Is that right? Yeah. Why did I say -9? When you plug that in, your meters should cancel and give you an inverse second in hertz, 4.61 times 10 to the, and you can either put hertz or you can put inverse seconds, I don't care. Got it? Questions?